Hello, this is Concrete Path. So for this lecture, we are going for the problems related to the shear stresses. Let's say that the section you have a square section, but the configuration is such that the neutral axis is you have the diagonal. The diagonal is parallel to the horizontal. So diagonal is parallel to the horizontal. That means along one of the diagonal, your neutral axis would be there. Along the diagonal, your neutral axis would be there. So this is your section, that diamond section. Let's say that neutral axis is that. Let's say this is the neutral axis. And let's take this height of h, and this one also height of h, and the total width of b, Say the dimensions of the square are AA, sides of AA, and you want to say at particular location of, let's say the configuration of that beam was in this way, that this is your section and beam is in this fashion. So your let's say the beam is cantilever, you apply some loads, and at a particular point A somewhere, you want to say what is the shear stresses at that point A. Shear stresses at that point A. We have the equation V and AYC by IB at A. So that means what's the shear force at that location? From the shear force diagram, you can have some shear force here. So that is V. And we want to say what is the first moment of area. The area, you can take area above that point A, or you can take area below that point A in the actual cross section. So point A is somewhere here. You can take the area above, or you can take the area below that point A. And the YC is the centroidal distance of that area. If you take area above, that is YC1, or if you want to take area below, that's YC2. So that is first moment of area. Either you take first moment of area of the first area, or you can take first moment of area of the second area. That's up to you. About the neutral axis you have to take. Then we have the I, that's second moment of area about the neutral axis of the entire section, that we have to calculate. What is the total moment of inertia about that neutral axis for the entire section, and we had to say what is the width at that particular location in the cross section. This was your point A. In the cross section, what is the width at that particular location? That's we write as width at A. So these parameters we need to solve for in this problem. Let's say you take in the cross section, you take a point A at a distance of y from the neutral axis, and you take some differential element of width of depth dy, and you want to say what is the total, because you have two options now. You got the point A. Now you can take area above, or you can take area below. It's up to you which area you can take. So for this one, it would become very calculation it would become a calculation, a hell of calculations. And for the first case, you can have easy calculations. So you can prefer first case, and its centroid is also easy to calculate. So we would prefer first part. So what's the area of the first part? Area above. There would be some centroid of that particular area. So if you take that area, there would be some width at A. At that point A, there is some width at A, and the height is total of h minus y. And by the symmetry, we can say what is the width at that location. Can you tell me what is the width at that location? That would be equals to, we know that B is per height h, with total width of B, that's for height, for a height of h, and I need for a height of h minus y. And the centroid would be somewhere here from the neutral axis at a distance of YC, that equals to y plus 1/3 of h minus y. Okay, y plus 1/3 of h minus y. So we got these parameters, and so that means we got the first moment of area, that equals to area of the triangle 1/2 b by h minus y into height of h minus y. So this is the area, and the centroid is acting at y plus 1/3 of h minus y. So you got this first moment of area of that particular area above that point A, but the moment is above the first that neutral axis. So we got the area A, that Q, Now we want to say what's the value of I about the neutral axis. So by the symmetry, you can say there are two triangles. They are meeting at neutral axis. If you solve for one part, then you can multiply for the next part by a factor of 2. You can say, let's say that neutral axis is somewhere here. Let's say that this is the neutral axis. This is the neutral axis. If you solve for the first part, you would say that you have some differential element dy, and you go from y goes from 0 to total height of h. You go from y from 0 to h, and you want to say what is the moment of inertia for this first part. That is integral y square dA, integral y square dA, integral y square dA, integral y square dA, integral y square dA. Yeah. So you go to some point. You go to some point at a distance of y. You go to some point. We know that we have the equation that I equals to y square dA. So y square is constant, and I would say what is the value of dA. So for that you take some element. Let's say the element is in the form of a rectangle with a depth of dy and width of b dash, such that I would say what is the value of b dash. So b dash would be equals to, by the symmetry, I would say b is for height of h. B, we know that this value is b. B is for height of h, and I need for h minus y triangle. So I need for this triangle h minus y. So we got the value of b dash. So the area small dA would be equals to, then we can write here small dA. So I can solve I neutral axis for the first part, that is equal to integral y square into b by h into h minus y and into dy. And your limits are from that you want to say about the neutral axis, you have small differential elements going from y equals to 0 to y equals to h, and you write from y equals to 0 to y equals to h, and you solve that, you can get a equation b by h into y square h minus y cube b by h into dy. So you integrate it 0 to h, so you got a value of by cube by 3 minus, then we have this one, y cube by 4 b by h 4. Then you substitute the values of 0 to h, so we got a value of bh cube by 3 minus bh cube by 4, that is 4 minus 3, that is 12. So we got a value of, for the first part, we got a value of bh cube by 12. So moment of inertia about the neutral axis for the first triangle, that is bh cube by 12. That's bh cube upon 12. bh cube upon 12. That means the total moment of inertia would be equals to, so I can say 2, that INA would be equals to twice INA1. So that would be equals to 2 times bh cube by 12. That is 2 times bh cube by 12. That is total of bh cube by 6. bh cube by 6. So I can substitute the values now. So I would say the shear stress equals to, I can write here also, the shear stress is equals to V Q by I neutral axis into width at that location A. So I got the value of Q here. So if you multiply V and then divide by BH cube by 6 and width at A. What is the width at A? The width at A, we know, width at A. So width at A equals to B by H into H minus Y. So you got this equation. Now you can simplify it. So I would write 3VB by H, and we have BH cube. So we got this part. We got V 2 6 BH cube B by H. We got these parts, and we have all one more thing, that's B by H. So you write B by H. So we got this one. Then we can say H minus Y goes 0, goes cancelled. So we are left with H minus Y into 3Y plus H minus Y by 3. So you got this value. So I would say I got a value of V. So B goes cancel. h goes. So we got value of v, and 3 also goes. So we got a value of v by bh cube, v by bh cube, and we have this equation of h square. I would write here also directly. I would say the total value of 3y minus y, that equals to 2y plus h. Then I would solve that 2yh minus 2y square, then minus yh, then plus h square. So you got 2yh minus yh, that is yh minus 2y square plus h square. So you got this part now. So we got equation of, so finally you can write the equation tau equals to v by bh cube yh minus 2y square plus h square. So this is our equation for the diamond section that shear stress at any point A at a location of y from the neutral axis. So now you plot that, you say this is our section, you want to say what is the shear stress variation along the depth of the cross section. Now the critical points are, this was your height of h. You want to say at y equals to 0, that means the shear stresses at the neutral axis. So you can write that the shear stresses at neutral axis at the rate of y equals to 0, that would be equals to v by bh cube 0 minus 0 plus h square. So that equals to v by b into h, v by bh. So what's the, if you convert it in terms of average stress, average shear stress, what is the total area? I would say, what is the total area? That is, for the first triangle we have 1 by 2 b into h. Then we have two triangles, so that is the total area of b into h. So I would write that equals to tau average. So your shear stresses is not maximum at the midspan, is not maximum at the mid. For this case, you have to see tau is not maximum at the mid, so that is equals to tau average. Now you want to say, now at what other location shear stress is maximum? So you want to say why is this location such that the shear stress is maximum? So if you want to say for tau to be maximum, so you want to differentiate it. I would say d tau by dy should be equals to 0. So that such that we would write here this part. So I would write as d by dy of yh minus 2y square plus h square. That should be equals to 0. So I would write that, which applies h minus 4y plus 0 equals to 0. That means at y equals to h by 4, from the neutral axis, you go to height of h by 4, or you go downwards h by 4. There you have maximum height, maximum shear stresses. You want to say whether it is maxima or minima. If you want to say whether it is maxima or minima, you double differentiate it. d2 tau by dx dy2, that equals to h. That equals to, for this part you have to integrate it again. So that equals to 0 minus 4. So negative value of. So that comes out to be equals to minus 4. That is negative. So that is maxima. That we can say it's maxima. Maxima value of h at h by 4. At y equals to h by 4, you substitute here at y equals to h by 4. From this equation, you substitute the value of that. I would write tau max at the rate of y equals to h by 4. That equals to v by bh cube. Then y goes to h by 4. And similarly, minus 2, y goes to h by 4. That means h square by 16 plus h square. So you solve this part. You write 4 inverse minus 8 inverse plus 1. That's 9 by 8. 9 by 8. So we got a value of 9 by 8 v by bh. That is 9 by 8 of tau average. That's equals to, that's 1.125 tau average. That's 1.125 tau average. So if you have the section, you know that shear stress is equals to tau average at the midspan. Let's say that shear stress is equals to tau average at the midspan. Let's say this is the tau average, and we know that if you go to some value of h by 4, and some value of h by 4, there you have shear stress maximum that equals to, let's say this is h by 4, let's say this part is h by 4, and similarly you go to h by 4 from the top side also, so there would be some value of that 9 by 8 of tau average. So you join those, so then after that we know that shear stress would be 0 at the ends. Shear stress is equals to 0 at the ends. So this is the variation. So this is the shear stress variation. This is the shear stress variation. So one thing I forgot, that why shear stress comes 0 at the ends? Why shear stress is 0 at the ends? We have the equation that V A Y by IT IB. If you say that, what is the if you take the point A on the at the end point, you want to say from the neutral axis you have some value of y, and there is some value of y, but what about the area? If you take the area above that point A, there is no area. Area equals to 0. That means 0 into yc, that is 0. So overall shear stress becomes 0. Now if you want to say I want to take the area below the point A, if you want to take the area below the point A, and that is equals to total entire area, that equals to total entire area, and we know that first moment of area about neutral axis, that equals to 0. So if you have this area, you want to say from the neutral axis, you calculate the first moment of area. I would say your yc equals to 0, because that centroidal axis equals to neutral axis. That means area is there, no doubt, area is maximum there, but your centroid is 0. So overall value of ay equals to 0. That means shear stress is 0 at the ends. Shear stress is 0 at the ends. Now we have one more problem that we can take one more problem. That's it. You have a rectangular cross section. 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 Let's wait for the second. Yeah. Hello. So where we reached that? Yeah. We had that next problem. Let's say you have this. You have the rectangular cross section. You have this rectangular cross section of width b and depth d. Now the concept thing is that you want to say how much out of that total shear force you are applied on that cross section, shear force of b. You want to say how much shear force is resisted by upper third part of section, cross section. So this part that we can have, upper third part, that is the depth of d by 3. So this part we have to say what is the total shear force this part can resist. I can say F shaded, how much force that shaded area can resist. So I would say that neutral axis is somewhere here. So I would say your area is going your area, concentrated area is that you have some point A and you take some area above that point A. So you take this area above that point A, and I would say the limits of y, the value of y is from this value to up to the maximum value of d by 2. So what's the value of here? Can you tell me what's the value of total is d by 2, and you have this limit from y goes from d by 2 minus d by 3, that's d by 6. So limits goes from d by 6 to d by 2. You want to say what is the total force this area resists? Let's say that let's if we take that element, if we take one element at a distance of y from the neutral axis, I would say what is the total force this part resists? How much this part resists out of that total shear stress? How much this part resists? I would say this value of dy. This is the depth of dy. Then I can say the total area of that dA equals to b dy. Total small area of dA equals to b dy, and I will say it will resist some shear force of dF. So it will resist some shear force of dF strip, a small force of dF strip, and that value of shear stress strip, that force would be equals to some shear stress it can resist at that particular location, some shear stress. We have the variation that shear stress equals to this, and particular at that particular element of dx we can have some shear stress. And that particular area, if we multiply that small area, and we can get the small force it can resist. So similarly, if you want to say what is the total force that upper third part can resist, I would say you integrate the total area, and your shear stress is also varying with the area. We know that shear stress itself is also varying, so we need to take the equation that includes the variation of shear stress along the section and plus the area that's also varying. So let's take that calculation now. We know that the equation of shear stress equals to VQ by IT IB, but in terms of cross section, in terms of rectangular cross section, we have one equation that we derived. We have that equation in terms of rectangular cross section. What is the equation? That is some sort of tau equals to 6v by bd cube and d square by 4 minus y square. This is the equation. Now you substitute the value here. The shear stress equals to, so integral 6v by bd cube. So that means total force in resisted by that shaded area for an area of bd by 3. So total force would be equals to integral 6v by bd cube d square by 4 minus y square. Then small area of that strip, that is b times dy. And the limits of that area are from, so your area is only this part, so your limits are from, you want to say how much force it resists. So your limits are from y goes to some value of d by 6 to d by 2. So we write d by 6 to d by 2, b by 6 to d by 6 to d by 2. Now you have to solve it, you have to calculate the values. So let's say this is 6v by bd cube, and we got this value b also outside, so we got a value of d square by 4, and after integrating you got a value of y also, then minus y cube by 3, y4 by 4, y cube by 3, and you put the limits that d by 6 to d by 2. So solving further, we can have that 6v by d cube, then we have this one that d cube, you substitute the value of d square by 4, and value of y goes from d by 2 to d by 6. Similarly, minus y minus 1 by 3 of d cube by 8 minus d cube by 216, 6 cube. So we got this part. Now you solve that, you can solve that 2 inverse minus 6 inverse into 4 inverse equals minus 3 inverse into bracket of 8 inverse minus 216 inverse, that equals to 7 by 162 into 6. So we got a value of that shear force resisted by that, we can say shear force shear force resisted by d by 3 part, bd by 3 part, upper third part, that equals to 7 by 27 of v, and that in terms of percentage, if you solve, that equals to 25.93%. That means that means you have this section 25.93%. That means we know that shear stress variation is in this form, shear stress variation in this form. So this part, so we have this shear stress variation tau, and we have this area d by 3, bd by 3. So this part registers how much shear stress. There is some shear stress variation tau v. I can write variable shear stress, and the area is bd by 3, and it registers some percentage of shear force, that is 25.93%, and this part also registers similarly 25.93%. That means the middle third part registers 48.15%. That's more. That's almost twice. That's almost twice with respect to the upper and lower part, bottom part. So that means shear stress is dominant in the middle part, or we can say in the mid section. But if you say what's the bending stresses, how the bending stresses vary with the cross section, I would say in the middle part you had lesser shear stresses. We have calculated one problem. We had one problem on that when we take the upper third part of that beam. Yeah, we took that. We said how much shear stress, how much shear force, how much bending stresses, how much bend that force shaded in that strip when we calculated that, and that was more force was resisting those upper parts were resisting more that bending forces, and the mid part was resisting less force because your bending stresses are less here, but the shear stresses are maximum here. So bending stresses are inverse, I can say, of shear stresses. If the shear stresses are maximum at the point, bending stresses are lesser at that point. With respect to that cross section, I'm not saying that if the bending stresses are less, your shear stresses are less. But with respect to the cross section, if you compare with the cross section, you got some value of bending stresses at a particular point, and if you compare with the shear stresses, the shear stresses would be lesser at that point. With respect to that cross section, I am talking about. So this is one way you can solve this problem. So this is the way you can integrate that the limits from d by 6 to d by 2. There is one more method. There is one more method that if you solve, we know that the variation of the shear stresses is in this way. Shear stress variation is in this way. So this is d by 3, this is d by 3, and this is d by 3. If you solve the shear stress value here and the shear stress value here, and if you assume that this is some rectangle, there is if you first solve that how much shear force middle part can resist, so that will be some shear stress into that we have some constant shear stress value of that the maximum we have 1.5 tau average. We can write 1.5 times tau average into width of into area bd by 3. So we got this one, and you subtract the value that this extra part we have. If you zoom it out, so we can have this area, that smaller area that we can have, it's a parabolic variation. That means it would be a parabolic spandrel, So I can get the area. I know that area equals to 1 by 3 of BH for this spandrel, and I know that it's acting for, let's say this I can say that it's acting for this area, for this depth of d by 6, and this is also d by 6. So I can say this is acting for the depth of d by 6, and I can calculate that is the difference of 1.5 tau average minus tau at that location of d by 3. I can get the value. Then I can subtract those values. Once I got the value of tau for that force resisted by the middle third part, then I can say the force resisted by the upper third part, upper 1/3 part, that would be equals to V total minus V mid and divided by 2. That would be also giving you V by 27 of shear force total V. If you want to solve that also, we can do that also. We can do that also. We can do that also. If we want to do it, let's do it also. Let's do that way also. Let's do that way also. So we have to get that. We have to get shear stresses shear force resisted by upper third part. So because of this part, how much shear force gets resisted. So we say that there is some shear stress tau at 1. I would write tau at 1 equals to, I can calculate that from the neutral axis. From the neutral axis, you go to some point limit of d by 6 to d by 2. So we have some point A, and we know that the shear stresses at this location would be equals to, 6V by BD cube into d square by 4 minus y square. The value of y here would be equals to, what should be the value of y here? Value of y would be equals to d by 6. Can you say that value of y is d by 6? D by 6. Can you say that value of y is d by 6? If suppose the value of y equals to d by 6, so that means d square by 36. So I got the value of shear stress at that particular location of, that means 4 inverse minus 36 inverse. 36 inverse. 36 inverse. And into multiply by 6. You got a value of 4 by 3. We got a value of 4 by 3. That's 4 by 3 tau average. Or we can write 4 by 3 V by BD. V by BD, 4 by 3 V by BD. And I know that the maximum shear stress would be at the neutral axis side point. So the maximum shear stress would be at this point, that is equals to 1.5 times V by BD. Now I want first, so here the steps are that first calculate, I want to calculate first that the shear force resisted by mid part, shear force resisted by mid third part. So that would be resisted, that area would be equals to this one. So this area, if I calculate first, I can calculate that. Let's assume that total, let's assume that the shear stress is constant value here. Let's assume the shear stress is constant value of this one, 1.5 times. So I can say shear force resisted by mid third, that equals to 1.5 V by BD, shear stress into area of BD by 3 minus, you have to subtract those spindles. Those spindles you have to subtract. These are 2 spindles, and the area of each spindle equals to 1 by 3 for the depth of d by 3, d by 6. For the depth of d by 6, this part is d by 6. So you have this spindle. Depth is d by 6. The difference of this is tau difference. With the value of tau difference equals to 1.5 minus 4 by 3 V by BD. That's the difference of the two. So I can write that also. 1.5 minus 4 by 3 V by BD. So you got the area 2 times 1 by 3 depth into this one, and you have to multiply also that, and also the width also. You have to multiply the width also. So finally you got this one. If you calculate the difference, you would calculate the difference. So I would say 1.5 by 3 and minus 2 by 3 by 1.5 by 3 minus 2 by 18 into 1.5 minus 4 by 3. Yeah. I got some value of 13 by 27 of total V. This goes cancelled, and this D goes with this D, B goes with this B. So we got a value of 13 by 27. V mid goes equals to 13 by 27. So if I say what is the value of V upper third, that's also V lower third, and that is equals to V total V minus V mid, and divided by 2. That's 13. That's 1 minus 13 by 27 by 2. That's 7 by 27 of V. Let's take one more. Let's take one more problem. Let's take one more problem. So we have this. We have a beam. We have this beam. Let's make it more interesting. Let's make it more interesting way. In a more interesting way, we have this beam of I section. We have a beam of I section. So this is a beam. This is a symmetric beam. That means your cross section, that the flanges, we call them top and bottom. We have those flanges, and mid part that we call it as web. That means the neutral axis is at the mid because of the symmetry. Neutral axis is at the mid. So we have the dimensions of that. We have the dimensions that this is 10, this is also 10, this is 150, and total of this one, this is 230, and this is also 20. So by symmetry, you say neutral axis is at the central axis, that is at the midpoint. You can directly say. Now you have this beam for the length of 4 meter. For the length of 4 meter. For the length of 4 meter. So you have this beam. So you had this beam. Now the beam is simply supported. The beam is simply supported. Let's say the beam is simply supported. Let's say the beam is simply supported. And a load is acting. And a load is acting. If you see from the line diagram, load is acting somewhere here at a distance of 1 meter from one side. And this part we have 1 meter, and this part 2 meter. A load of 30 kilonewton. Load of 30 kilonewton. Now our worried cross section is that at some x value equals to 1 meter, there are some points on the cross section. Let's call them as point A, point B, point C at the neutral axis, point D, and point E. You need to say what are the stresses or shear stress variation along that cross section. Shear stress variation. That's, you need to calculate tau A, tau B, tau C, tau D, tau E. So you need to solve those values. Now the section has been predetermined that at x equals to 1, you had to get the shear force value here. Can I get the shear force value here? Can I get the shear force value here? Can I get the value of shear force here? That equals to 30 into 1 by 4. 30 into 1 by 4, that's 7.5. Positive 7.5. That means the shear force here is 7.5 kilonewton. So we got the equation that tau equals to VQ by IT. So we have the 7 kilonewton. Now at particular point A, B, C, D, E, your value of AY also changes. And I neutral axis, that's fixed value. You need to solve I neutral axis. And before that, you need to solve the location of neutral axis. We know that by symmetry, your neutral axis is at mid. You can verify that also if you substitute the values of all those areas and their first moment about the neutral axis where you want to solve that neutral axis. So you can get the value of location of neutral axis. That would be at the mid span. I would say neutral axis is at the mid span, is at the mid section, such that this is Y, and neutral axis would be at 230 plus 10. 230 by 2 plus 10, that's 125. 125 mm. Now you want to say what is the INA? What is the value of INA? That would be equals to, let's take the section. Let's take the section in this way. You have this section. We have this width of 10. This is the depth of 10, 10, and this is also 10. This is 150. Width of 150, and depth of that, this one is 230. So if I solve that, I would say I can directly solve in this fashion, that assuming that it as a rectangle, then I can solve that 250 cube by 12 into width of 150, and minus that, subtract that, this smaller, so those rectangles, because your section is symmetric. That means these two areas are also their centroid is along that neutral axis. Their centroid is also along the neutral axis. I would say this dimension would be equals to 2 times, I would say, 150 minus 10, that's 140, into depth of 230 cube by 12, and I get a value of I, that is equals to 48 point. Yeah, actually the calculation is that you have the dimensions of this one. You have these dimensions equals to 5 mm. This is 5 mm. 5 mm. That's 5 mm. Next others are 10, 10. Yeah, 10, 10, 150, 250. Yeah, 5 mm is there. So this is 5 mm. So this is 5 mm. This is 5. So you have to say this is 150 minus 5. That's 145. 145 into 230 cube by 12. So you got a value of 48.2945833, 10 to the power 6 mm power 4. So we got this value INA. Now we have this so we got this value. This is fixed. Shear force is also fixed at that section at 1 meter from support A, and this value is variable for the points A, B, C, D, E, and we have width also varying at that point A, at that point B, that's A, B, C, D, E. So you need to solve for all those points. Let's solve for the point A. Let's calculate for the point A. I would write shear stresses at point A, that equals to V by I, and B. What is the area above that point A? If you take the point A, what is the area above that point A? That is 0. So I can write area equals to 0 into Y. So I get a value of shear stress at A equals to 0. Now if you want to take area below that point A, you would still get the value of that AY equals to 0, because your centroid of that area would be at the neutral axis. So you would get that Y equals to 0. So finally your shear stress at A equals to 0. And similarly, you can say tau at point E, that's at the bottom. So shear stress at the E, that's also 0. Because your area below, that is also 0. Or if you want to take area above, that, then you have to take the centroid of that area also about the neutral axis. That's also 0, because you are taking the entire section. So you got the stresses at A and E equals to 0. Now let's talk about the stresses at the point C. Let's talk about the stresses at point C. Tau C. So we write shear force of 7.5 kilonewton, and moment of inertia about the neutral axis was equals to 48.29 into 10 to the power 6 mm power 4. And we have to get the width at that location. What is the width at that location? So width at C, I would say width at C equals to 5 mm. So you multiply that 5 mm. Now what is the area? That first moment of area, you can take area above or you can take area below. You have two options. For the point C, because of symmetry, it's at the neutral axis. Both areas have the same meaning. You can take either of the two areas. So let's take the area above. So we have this width of 5, this depth of 10, total of the width of 150, and this part, this equals to 115. So you can say its centroid is somewhere here and its centroid is somewhere here. So you need to take the that moment of areas about the neutral axis. So let's calculate that AY bar. So your AY bar would be equals to, that is summation of AIYI. So that would be equals to 115 into 5. That acts at 115 by 2 plus next area is your 150 into 10, and that centroid is acting at 115 plus 10 by 2. Centroid is acting at 115 plus 10 by 2. Then you multiply it in this way. So you got a shear stress value tau C equals to shear stress at C equals to 6.617 megapascal. 6.617 megapascal. Now, if I want to say, if I want to take the, if I want to take the point B and D, for the point B and D, let's calculate for the point B and D. Let's calculate for the point B and D. Let's calculate for the point B and D. For the point B and D, for the point B and D. So this part is constant. That V by INA is constant. Now you want to take tau at B. Now tau at B. So I would say this is your point B. You have two options. Either you can take this area or you can take this area. It's up to you now. If you take this area, it's up to you. That is neutral axis. Then you have to take. So this you have to. This is your neutral axis. Then if you take this as positive, upside as positive, and this you have to take this side as negative, or you can take this side as negative, this side as positive about the neutral axis, because you are going from neutral axis above, or you are going from neutral axis below. So you have to say the sign also. You can keep the sign for the particular sign for either of the side. So but for the first case you have easier calculation. Area is fixed, a smaller area of rectangle, and the centroid is also known from the neutral axis. So we can take the area 1. So if you take the area 1, I would say what's the first moment of area about the neutral axis. So I would say this is the, we have a width of 10, we have a depth of 10 and width of 150, and the centroid neutral axis is here, and I would take the yc equals to this one. Yc equals to, point is B, but the area above you have to take up to that the centroidal distance. That is 115 plus 5, 115 plus 5, 120. So I can solve that. That's 150 into 10 into, we can write in this way, 230 by 2 plus 10 by 2. That is 120. So we got the area AY bar, first moment of area. Now you want to take width at B. Width at B. What is the width at B? What is the width at B? So you have this point B. That's at the junction. So width B is at the junction between the flange and the web. So which width you can take? So we can take both widths. We can calculate separately. Let's take the width just before that point B. Let's take that in the flange. I would write tau B in the flange, tau B in the flange, tau B in the flange. And for that you have to take B, width at B in the flange. That equals to what is the width in the flange? That is 150 mm. And you can solve that. Shear stress would becoming equals to 0.1863 megapascal. And now if you want to say what is the shear stresses in the web, what is the shear stresses in the web, that would be equals to shear stresses in the flange for the width of BBF, but I need for the width of BBW. So because other parameters are fixed at point B, this is fixed, and this is also fixed, because only your width changes at the junction. Either you can take flange width or you can take width of web here also. Here width of web. So other parameters being fixed, you can say you have this parameter, you multiply with this overall stress you got for the flange, and you divide based on the web, width of web. So you calculate that. You can write 0.1863 megapascal into your width in the flange was 150 and width in the web is equals to 5. So you got a shear stress value of 5.59 megapascal. 5.59 megapascal. 5.59 megapascal. So you got the shear stresses at point B. Similarly, you can say that shear stresses at point D are equals to shear stresses at point B because of the symmetry. Because of symmetry, we have the same shear stress values at point D in the junction, and that means in the web also, in the flange also, we have the same values. So let's make the variation of shear stresses now. Let's take the section. So this was your I section. This was your I section. So this was your I section. This was point A, point B, point C, point D, point E. And this is your reference line. We have the shear stresses at A and E equals to 0, and the shear stresses is maximum at the neutral axis. So that is value of tau C. That was equals to, that we have shear stresses at C. That value equals to 6.617 megapascal. 6.61 megapascal. And at the point B, we had two shear stress values. One was in the web, next one was in the in the flange side. So this is point B. We have two values. There is a variation of parabolic variation. We don't know the values at their 2 points. So if you talk about the shear stresses in the flange, shear stresses in the flange is 0.1863. 0.1863. Let's say this value is 0.1863. Shear stresses in the flange. Let's say this is the flange here. This is the flange. Shear stress in the flange is 0.1863. But shear stresses at point B, but in the web, that equals to 5.59. 5.59. That means just below that point B in the web, 5.59. So that is 5.59. So there is a sudden rise of that shear stress, linear variation, I can say. A sudden rise, sudden jump of the shear stresses because your cross section changes from flange to web. Your cross section is reducing. That means your stresses vary. That means stresses increase suddenly because your area changes suddenly. That's why your cross section, that's why your shear stresses also vary suddenly, tau, because your tau inversely proportional to width B. So your B decreases, that means shear stresses increase. So you got the shear stress value here, and you join the 2 points in a parabolic curve. Similarly, you can have point D also here. So shear stress value would be same if you can solve that also. So then after that, there is a rise, 5.59, and you have this join. You have to join them in this way. So you got the shear stress variation. So this is your tau variation along the cross section depth. Now, if you want to take one more problem, let's take that problem there. Yeah. Let's say that you have a simply support beam, and there is a UDL for the entire length. UDL. So for the length of L, if you draw the shear force diagram, there would be some shear force diagram of that. This is WL by 2, and this is your shear force positive, negative, and bending moment diagram would be in this way, WL square by 8 maximum. So, but if you take the entire beam in a 3-dimensional manner, so I would say this is the length and that depth. This is depth. This is length, and there is some cross section B into D. So this is your beam now. Now you are applying a uniformly distributed load. So this is your load of UDL. Then we can say this is your W, kilonewton per meter, and that equals to 2 kilonewton per meter, let's say. Now you want to say what is this different state of stresses? Now you take some points. Let's call this point as A, this point as B, this point as C, and this point as D. This is our neutral axis. and this one is your neutral surface. I can say this is neutral surface. So we have 4 points. A and C is above the neutral axis and B and D is below the neutral axis. And for the bending moment, that's positive bending moment, that we have sagging curvature. That means the stresses would be top compressive, bottom tensile, bending stresses, sigma BT, sigma sigma BC, sigma negative, sigma positive. So because of the positive bending moment, we have positive that's tensile stresses in the bottom side. B and D is having tensile stresses. So your B and D is having tensile stresses, and A and C is having compressive stresses. Now, if you want to represent a point A by general state of stress, you want to say this is your point A. What are the stresses acting on this point? So I would say because of the bending stresses, there is normal. So bending stresses are actually normal stresses that are perpendicular to the surface. If you have this plane, the bending stresses are perpendicular to the surface. That is, it's a normal stress of sigma. I can say sigma compressive. Because it's compressive, I would write some value of sigma. So I can write that it's a compressive stress acting on that point A in the horizontal direction. So sigma, there is some sigma acting on this direction. So compressive stress. Then after that, you want to say what is the shear stress acting on this point A? I would say, let's say this point is at some distance. So this is your mid point. So this is your mid of the beam. I would say, let's say this is the mid of the beam. Then I can say this is the point where A and B is there. So A and B is somewhere here, and similarly C and D is somewhere here. So I can write for A, you have shear force positive. That means if you have this element, you have shear force positive. That means your shear force is positive in this direction. So I can, if your shear force is in this direction, and I can make the shear stress, I can make the shear stresses now. I would say this is your shear stress tau. And based on this, I know that the if this is V, let's say this is V positive, but the shear stresses, we know that shear stresses, if the shear stresses are in this direction, that means they are negative. Tau is negative. That means tau is negative, because you want to say what is the value of this one? I would say draw perpendicular to it, draw the normal, so it's acting in positive x. I can name this value tau x, and it's acting in the y direction, so I can write tau xy. But the y direction is in negative y, so I can write minus y. So your plus into minus becomes negative. So your shear stress is negative. Final value of shear stress, that is negative, minus tau. Similarly, you can have shear stress in this way also. So your state of stress on that point A would be in this fashion. Similarly for the point B, you have this point B. On this point, based on the bending stresses, we say that we have tensile stresses on the point B. There's some tensile stresses on that point B. And point B is in the positive shear force side. So positive shear force. Based on this, we have this shear force diagram. You have this shear stress downwards from this side. So tau would be negative. Tau is negative. So tau is negative. For A also tau is negative, but shear force is positive. But tau is negative. And for the point C, this is your point C, and on this your compressive stress is acting, and from the SFD you have shear force value of minus. So shear force is minus. That means in this fashion. So your tau is positive. And for the point D, you have bottom, that is tensile. For the point D, you have tensile stresses. And point D is in the having shear force negative. So you can show the sign also that. So you have this shear force, that shear stress also in this way. So that means in this way. So shear force is positive. So we got the general state of stresses for those four elements. Now you take that problem that Let's call it as unsymmetrical I section. You take unsymmetrical I section. So you have simply support beam, 8 meter simply support beam, and a UDL of 20 kilonewton per meter. And the cross section of the beam is in this fashion. So upper top, that is equals to 60, and bottom side we have 120, and the depth of those flanges is equals to 20, and the depth of that web equals to 150. This is 150. So this is also 20. This is also 20. So based on this fact, I would say this is unsymmetrical I section. So I need to solve for the location of neutral axis. So let's take the neutral axis from the top at a distance of y bar. So neutral axis would be at y bar. So centroid 1, centroid 2, centroid 3. I can write that would be equals to 20 into 60 into this centroid is acting at 20 by 2, that's 10. Then plus for the next part, centroid is acting, I would write second area is 150 into 20, and the centroid is acting at 20 plus 150 by 2, that is 95. And for the third area, we have third area of 120 into 20, 120 into 20, and centroid is acting at 170 plus 10. So you divide the overall value with the total area that we have. Total area of, what is the total area? That is 1200 plus 3000, then 2400. So this is the total area, and you got a value of that location of neutral axis is at a distance of 110.45 mm. So from the top you had to go 110.45. So the total, I would say total depth is 190. So you need to go up to the 110. This part is 75. This part is 20. This is 75. That means neutral axis is somewhere here at 110. So this is neutral axis. So I would say this is equals to 110.48. That means the bottom side, that part would be equals to 190 minus 110.48. That would be equals to 79. Let's say 79.455. 110.48 minus 190. 79.52. Let's write 79.52. 79.52. Now you want to say what is the moment of inertia about that neutral axis. So you have to solve the moment of inertia about the neutral axis now. So you got this value. Now you have to say what is the moment of inertia about the neutral axis. Let's solve for the first part, that INA equals to, for the first rectangle we have BD cube by 12, BD cube by 12 into AD square, AD square. What is the value of D for the first case? So neutral axis is here. So this is your D1. So D1 equals to, total was 110.48. You subtract the distance of 10 minus 10, then you do square. So for the first part, we are done that. So now for the next part, let's say that this is a rectangle. What is the INA about that? It's about its own neutral axis, about the centroidal axis for this rectangle. That equals to BD cube by 12. So that is BD cube by 12, BD cube by 12, BD cube by 12 plus, and we have this area, we have this rectangle, its centroid is at, so from the top I can say, from the top, let's say this was your top, that this was your 60, that means at the top. From this point, your neutral axis is at, firstly I would say, where is the centroid of that area? For this area, where is the centroid from the top? So I would say that is at a distance of 20 plus, that's at a distance of 20 plus 150 by 2, that's 95. Okay, 95. at 95 from top, your centroid of that area is there. But from the top, if you say from the top, the neutral axis is at a location of 110.48. So that's at a location of 110.48. That means the D value of D equals to difference of the two. So I got the value of D equals to, I can write D equals to 110.48 minus 95. Then I do square. So I can write also area square, AD square. So your area equals to 150 into 20 into D square. Okay. This is the solution. Then after that, we have the third area. This one that we can write as BDQ by 12. BDQ by 12 plus its centroid is here. And if you have neutral axis at a distance of 79.552 from the bottom, and the centroid for this one is at 10, so I can write the area, that's area 120 into 20, and the centroid distance is 79.52 minus 10 whole square. So your moment of inertia would be equals to 30.1786 10 to the power 6 mm power 4. So you got this moment of inertia. You got the moment of inertia. Now the problem says that you have to get the shear stresses. You have to get the shear stresses at the location of, you have the cross section. Okay, you have the cross section. This was your cross section. 60, 120, 20, 20, 20, and 150. So you want to say what are the different what are the values of stresses at point A, point B, point C, point D, and at the neutral axis. So you need to solve that. Shear stresses at A, B, C, D, and neutral axis. So we have the equation. That tau equals to B by I neutral axis, and B at any point I, and area I, YCI. Do you know that? We have this equation. So for particular locations that shear stress at a particular location of I, that is given by this equation. Now, if you talk about point A, what is the value of shear stress at point A? So I would say shear stresses at A is equals to shear stresses at D equals to 0, because area above equals to 0 or area below equals to 0. Or if you want to take area, we have some area, but YC is 0 because that centroid is at the neutral axis. So you have different options. So your shear stresses is 0 at the ends. So we got the shear stresses 0 at the ends. Now if we talk about point that neutral axis, let's talk about neutral axis. So for the neutral axis, you have two options now. Either you can take this area, or you can take this area. Option is up to you. Right. Option is up to you that. So you can take any of these two area. Now, about the neutral axis, you have to calculate the first moment of area. Let's take the area that I have already. Take that yeah, I can take the first part. If you take the first part, then I would say there is some centroid 1 and there is some centroidal distance to y2. So I can solve for that. So let's try that. Shear stresses at neutral axis equals to a shear force of what is the shear force? What is the shear force value? So we had some beam 20 kilonewton per meter, and 8 meter was length, and you are given that you calculate the shear stresses at that different locations of A, B, C, D, E at 3 meter from support A. So you need to solve for the reactions at the support at 3 meter from support A. Let's say the shear force at the support is this one, that is WL by 2, and it is linearly varying. And I would say shear force here would be equals to shear force V3 equals to W into L by 2 minus W into X. That is 24, 80 minus 60. That's 20 kilonewton. So the shear force here would be 30 kilonewton, 20 kilonewton. So you substitute the value that shear force equals to 20 kilonewton, 20 kilonewton into your area, summation of those areas, first amount of areas about the neutral axis. So I would write that also. So we have this area. Can you tell me what's the total area? So we have this 20, we have this 60, and this value, we have this difference of 110.48 minus 20, because neutral axis was at distance of 110.48 from the top. So the difference, this value would be equals to 90.48, 90.48, and the width we have 20. So I can solve that. But the value of y should be from the neutral axis now. You have to take the value from neutral axis. Y should be from the neutral axis. So let's calculate that. Let's calculate those values. So I will write your area 1, that is 20 into 90.48, and that acts at 90.48 divided by 2, plus your second area is 20 into 60, 20 into 60, and that's acting at 90.48 plus 20 by 2. Okay, that's acting at 90.48 plus 20 by 2. Now you have to divide by INA. We already got that value. You substitute that into your width at that location. What is the width at that location? What is the width at neutral axis? Width at neutral axis, that equals to 20 mm. So you got the shear stress value at the neutral axis equals to 6.705 megapascal. So you got the shear stresses at the neutral axis equals to 6.705 megapascal. So you have this beam, and neutral axis is somewhere here, and you got a value of 6.705 megapascal. And shear stresses at the end is equals to 0. So you want to say, now what's the value of shear stresses at the junctions B and C? Let's say let's solve for the section B. Let's solve for the section B now. Let's solve for the section B. For the section B. So I would say shear stresses for the B, that equals to shear force of 20 kilonewton into what is the area you can take for the point B. Which area you can take? Either you can take area below or you can take area above. So this is point area above. It's easy. So you have the centroid for area above. This is point B, and area above that point equals to 20 into 60, and the centroid is at a distance of 100.48 minus 10. That's 100.48. 100.48. So this YC equals to 100.48. So I can write area is 60 into 20 into 100.48, and divided by INA. You already calculated that, and width at, now the width at B, but we have two options now. Now you want to say at the junction we have two options. Let's take the width. Let's calculate for the shear stresses in the flange. Shear stresses at B, but in the flange part. So I would write width at B in the flange, that equals to 60 mm, and you can get the values of shear stresses equals to 1.33 megapascal. 1.33 megapascal. And similarly, if you want to say shear stresses in B, but in the web part, that would be equals to shear stresses in the B in the flange part, and you multiply this width BF equals to 60, and you divide by the actual width where you want that shear stresses. That's a shear stress BBW, that equals to 20. That means your shear stresses increase by 3 times. That value equals to 3.99 megapascal. So by decreasing the width, so your shear stresses got increased. So I can show that those two values, 1.33, 3.99. So you had point B somewhere here, So you had a value of 1.33. Then after that you had a sudden drop, a rise of 3.99. You had a sudden rise to value of 3.99. Then there is a variation of parabolic. So this variation is parabolic, but after that this is straight. So then we can join this point also. So this is 6.705. Now from the other side, because beam is not symmetric, that means stresses at B are not equal to stresses at C. I can't directly say that stresses are same because your section is not symmetric, so I had to solve for the stresses at C. I had to solve for the stresses at C. For the stresses at C. So we had the stresses at C that we can write. So we can take the area. Either we can take area above or area below. Either you can take this area or you can take this area. So I can take this area because your calculations will become easier. So they have this area with a width of 120, depth of 20, and the centroid is at a distance of. So we had the actual distance was here 79.52, and I can say this value of YC would be equals to 79.52 minus 10. So 69.52. I can write that area was equals to 120 into 20, and the central distance of that area about the neutral axis that equals to 69.52. So, and you divide by width at C, but we have two options now. So you can say shear stresses at C, but in the web part, shear stresses in the B at the C, but in the web part you have to take that width at C in the web part that equals to 20, and you can solve that. You got a value of 5.53 megapascal. Now similarly, if you want to say shear stresses in the shear stresses in the flange, shear stresses at C, but in the flange part, shear stresses at C, but in the flange part that is equals to shear stresses at the point C, but in the web part into this width BCW equals to 20, and you divide by BC flange that equals to 120. So your value is decreased by 6 times. So your value got decreased by 6 times, that equals to 0.922 megapascal. So you can show those values. So this is value of 0.922. So you have this value of 0.922. So some value of 0.922. Then after that it increases to 5.53. 5.53. This is 5.53. Then after that you can join the 2 points. So this is the variation of shear stresses for this beam that says unsymmetric I section. That's unsymmetric I section. So let's take the final problem. I think, yeah, we have two problems that. Let's take the problem that is saying that we had that beam in the form of diagonal cross section, such that neutral axis is parallel to, such that along the diagonal you have neutral axis, or diagonal is parallel to horizontal. One of the diagonal is parallel to horizontal. So you have square of side equals to 100 mm. Your 100 mm side, and I can say what is the width. Can you tell me what is the width? I would say that is 100 root 2. Can you say that? This is 45. I would say this is 100 root 2, and value of h would be equals to 100 by root 2. Can you say that? Based on the derivation, I can keep those parameters in that parameter fashion. So I would say this is h, and this is also h, 100 by root 2, and width of 100 root 2. So I got these three values. I got these values. Now the question says that we have this bar, and and a shear force was applied. Shear force of 600 kilonewton was applied at that cross section. So we need to say what is the shear stress variation, and the value of tau max, So we have the equation. We know that the variation, how the variation is there. So one of the equation we got that finally shear stresses was equals to V by BHQ and H minus Y 2Y plus H. Either you can do this way, or if you remember those results, then you have derived during that concepts. So I would say we have the variation that at the neutral axis we have shear stress value equals to tau average. Then after that it increases to a depth of h by 4 at h by 4 from both the sides, and then it decreases to 0. So the maximum value we have tau max equals to, we got the value here there at that time, tau 9 by 8 tau average, where your tau average equals to V by BH. So if you write that shear force was equals to 600 kilonewton divided by BH. B is your 100 root 2 into H is your 100 root 2 and square. So you got a shear stress average value of I think 60 megapascal. And if you want to say 9 by 8 tau average would be equals to 67.5 megapascal. So those values you can show in the diagram. You can show the values in this way, that this is your 60, and after that you had some 67.5. Similarly, you have from this side 67.5. So then it decreases in a parabolic fashion. So this is your shear stress variation. Let's take the final problem. So we had a simply support beam with the UDL for the entire length. Now with the cross section width dimensions BD, and you had to say that at what critical length section, at what critical section of that length L, let's say this support A and B, from support A, at what critical location of X your tau max and sigma max are reached simultaneously. That means your maximum stresses of shear and maximum stresses of bending, they reach their maximum value simultaneously. What should be the location of X? So the problem is saying that you have to get those maximum values, but I know from the bending stress formula, flexural formula, that maximum stress is at the extreme fibers, and the maximum, I can say sigma max equals to m y by I. Do we know that maximum stress equals to m y by I? So for maximum stresses, I would say you should get maximum moment and you should get y max. Can you say that for maximum stress you need maximum moment and maximum y max? So for the rectangle section, y max equals to d by 2, I can write, and m max, keep it as it is, and we have d by 2, and value of I neutral axis is equals to bdq by 12. Now what is the value of m max we can have? What is the m max we can have? How much maximum stress we can have? From the BMD, if you draw the BMD, how much maximum bending moment we can get? WL square by 8. And how much shear force maximum we can get? That's at the supports. So maximum bending moment is at mid and maximum shear force is at supports. That equals to WL by 2. So if we solve that, if you substitute the value of m max equals to WL square by 8 and value of d by 2 is here, and we have bdq by 12, that is finally can say WL square by 8 into divided by bd square by 6. So you got this value, sigma max. And what's the tau max value we can have? Based on the cross section, do you know what's the maximum shear stress we can have? Is it V by BD? Is it V support by BD? Or is it something else? Is it something else? Is it something else? What is the maximum shear stress we can have? It's not only V by BD. This was your V by BD. This is not only V by BD. That's maximum shear stress we can have at the midspan, at the neutral axis of that section. That equals to 1.5 V by BD. And how much V max we can have? That maximum V we can have, that equals to WL by 2 and divided by BD. So you got this value 3 by 2, 3 by 4 of WL by BD. So this is your tau max. So you got these values. You got these values. Now, one thing is that if you write M by V, M at any x and V at any x, because we don't know the value of x where that critical section would be here, which would be there. So if you write moment equation in terms of mx and shear equation in terms of mx vx, so we can have that equation. Let's write moment equation. I would say your reaction of WL by 2, the support would give you reaction of WL by 2. Then we can write WL by 2 into x, WL by 2 into x minus WX square. Can we write WL by 2 into x minus WX square by 2? And what is the shear force shear equation at that any particular location of x? I would write shear at support minus linear function of loading Wx. So you got this value of mx and vx. So if you solve it, you can get a value of Lx minus x square by L minus 2x. So you got moment x, mx and vx, and we also got that sigma max and tau max. Sigma max and tau max. So one thing is that if you take m max in terms of sigma, if you write moment at any x in terms of sigma, I would write sigma INA, sigma I by y. So that is sigma max and BD square by 6. M max equals to sigma max into BD square by 6. If you substitute that value here, that I want sigma max at that particular location of moment mx, I want sigma max there. I want that sigma should be maximum, and you multiply with the section modulus BD square by 6, because m equals to sigma z. And similarly, your shear force, your shear force at a particular location, we know the equation shear force equals to that 3 by 4 of, or we can write in terms of this one, 1.5 V by BD. So your shear force at any x, that should be maximum. Now we want shear force at any particular location such that it would give me a tau max. It would give me a tau max into, I would say, BD by 1.5. So this I have to write tau max BD by 1.5. Tau max BD by 1.5. Tau max BD by 1.5. So you got this one. Now we had to get the critical location of that x. We got the equation in terms of sigma and tau. We said that sigma should be maximum and tau should be maximum. So now if you substitute the values of when sigma would be maximum and when tau would be maximum, I would say sigma is maximum at the value of WL square by 8 into 6 by BD square, this value. If I substitute that, I would say sigma max equals to WL square by 8 into 6 by BD square, and we have already provided that BD square by 6, and you divide by tau max. Already I know tau max equals to 3 by 4 WL by BD, and you multiply BD by 1.5. You multiply by 1.5. So you get that equals to Lx. I can say that equals to Lx minus x square divided by L minus 2x. So from this we can eliminate few terms. let's say WL goes, WL goes. So we are left with L here. So also we can say BD square goes, BD square goes, BD goes, BD goes, and I would say 6 and 6 goes, and 1.5 ones are, 2s are, and 2 ones are, 2 2s are. That means 2 ones are, 4s are. That means 1 by 4. We are left with 1 by 4, and there is some length L. There is some length L, and this length also goes. So we got only 1 by 4 value here. So we got this value of 1 by 4. Is it correct? Yeah, 1 by 4. Yeah, there. We are left with this L because we said WL and WL square. That we are left with L. 1 by 4 of L. Now if you solve that, you got Lx minus x square equals to L square minus 2x divided by 4. So you got a value of 4Lx minus 4x square minus L square minus plus 2x plus 2x. Is it 2x? 2xl, 2xl plus 2xl. Yeah. So we got this equation equals to 0. Now you solve this quadratic. So you solve it. So you got a value of 4x square, then plus 6xl minus L square equals to 0. So your value of x equals to 1.309L and next value of 0.191L. So this can't be, this is not possible. So I would take this second value, that at a distance of, so this length is L. That means at a length of x equals to 0.191L, your sigma max would arrive and tau max would arrive simultaneously. See, we could have directly solved it, but the condition we had to keep in mind that sigma max should be in the equation and tau max should be in the equation. That's why we converted it into this one and this one. Otherwise, we could have directly said that we want for the sigma max to be maximum, we want m max to be there, and for tau max to be there, we want v max to be there. So by this configuration, by this setup, we can say for particular mx and particular vx, that was WL by 2 into x minus WX square by 2. That was shear force was WL by 2 minus WX. That should be equals to maximum bending moment. Maximum bending moment we can have WX square by 8, and this maximum shear force we can have WL by 2. But we have to keep that in mind also, that we should not miss any other thing. Yeah, we can solve it this way directly. We could have solved in this way. So then we could have solved that, and we got a value of Lx minus x square by L minus 2x equals to L by 4. So same procedure we can solve 4Lx minus 4x square equals to L square minus 2xl. This was the direct procedure, but the thing is that you have to convert that sigma, that sigma max, how much value of sigma max is there, m max BD square by BD square by 6, and that tau max is not only V by BD, that's 1.5 tau, that V by BD. You have to keep that also in mind. Based on these two parameters, you should have solved that problem. Okay. So this is the end of that, the first topic, first lecture for this. Actually, it's second lecture for the shear stresses. Thank you for watching the shear stresses. I hope the stresses would remain lesser than the permissible stresses. Okay, thank you for watching.